Be a slightly longer webinar than we normally do, so indeed, let's get started. And as Mafalda already mentioned, managed, we're gonna talk today about performance estimation under covariate sheet without target data, which is also the boring part of the title of the paper we wrote recently. It's on arXiv, and Mafalda will share the link at the end of this presentation, so you can take a look if you want. It has not been accepted anywhere else, so we're gonna ask everyone to not share it too much. But let's first get started with the actual paper. So what we did is we evaluated a couple of algorithms that are used for performance estimation. So trying to estimate what is the machine learning performance, such as accuracy, AUROC, or F1, for real life data on around 600 data sets. And we compared the results. And one of the things we also did is we added our new algorithm called M-CBPE, which stands for Multicalibrated CBPE. And one of the reasons we actually wrote this paper is, of course, because M-CBPE outperforms all other methods. Quick summary of what you're seeing here. This is basically the most important part of the paper as well, and it shows the results. So what we did here is we estimated the accuracy of 600 models that then we averaged in one way or the other, the AUROC or ROC AUC of the 600 models trained on 600 data sets, and F1 of those models. And your default way of predicting performance once you deploy your models to production is to just assume that the performance is going to be equal to the test set. So we take what is the performance of the test set, we call it the constant here, and we just assume it never changes. And we can also then measure how good that constant performance is at actually predicting accuracy, AUROC, and F1. And you can do it via modifying slightly MAE. You can just treat it as typical mean absolute performance, mean absolute error, or RMSE, root mean squared error, and we did the same thing for the other metrics. Then we just divided the error that we got by constant performance to make sure that these numbers are a bit more meaningful. And what you see here is basically we have 6 methods that are available either in literature or in open source solutions. The first 3 we're not going to be discussing too much today, because as you can see, they strongly underperform actually. And in some metrics, such as a ROC AUC, if evaluated via root mean squared error, they're actually worse than just constant prediction. So they are worse than not doing anything. So we're not going to be talking about them, but we will do a very deep dive into 3 other metrics. One of them you might already know from NanoML open source, which is CBP, confidence-based performance estimation. Another one is importance weighting, which is a metric or an algorithm that has been developed in, I think, 2019. And Mafalda will also share the paper for that later on. It's also cited in our paper. And then we have our multi-calibrated CBP. And as you see, for any metric we choose, for any evaluation method, it is the best out of the flock here. So this is kind of the teaser of what we are about to see. But from now on, we're not going to be focusing on the paper too much, but instead we'll try to focus on the algorithms and step by step build the intuition of why performance estimation is possible, how is it possible, and then we're going to talk about the actual algorithms, build the intuition, their strengths and the weaknesses, and we'll also show some results on specific data sets just to give you a visual understanding of what's going on and how well we actually can predict performance. So this is actually the agenda. I already covered it. So just step by step, why is performance estimation vital? Why do we even need to do it or should do it? How is it possible? Because you should normally just take all the information to predict your point prediction, your classification. Turns out it's not that simple. And then we're going to talk about how we can come up with some kind of uncertainty measure and then actually map it to our metrics, to our performance, such as F1 score, etc. And this is basically our CBP algorithm. Then we're going to figure whether we can consider our current distribution in additional ways, and that's where importance weighting comes in. And it's going to give us a very important tool that will allow us later on to improve CBP and multi-calibrated, and then we'll put it all together in the last step with M-CBPE algorithm. So let's get started with the first part. Why is performance estimation vital? So this is kind of obvious, but I'll just walk you through it in case it's not clear for someone. For as data scientist or machine learning engineer or any person that works with data and develops models, what you actually want to do is maximize the business impact of your models. You develop models, this is your impact on the company, this is how you bring value. So this is your main KPI. But business impact can only actually happen once you deploy your models to production. So what we're going to do is when you develop your models, you're going to use some kind of ML metrics like accuracy, recall, precision, etc., or F1 as a proxy for that business impact, because it's normally very hard to estimate your exact business impact. And we need to know them to measure that business impact. But unfortunately, once we deploy our models to production, if you predict events or classes, numbers far in the future, you don't have the labels to immediately evaluate the performance of your models, and you need to wait even up to a year to do it, which sometimes is very risky if your use case is important to the business. In other cases, if you want to automate some kind of task, again, the labels would not be available, because to get the labels, you would need to do the same exact work manually, which kind of defeats the purpose of automating it with AI in the first place. So the labels are not available, but maybe we can somehow estimate them anyway. And let's try to build an intuition of how it's actually possible now. And before we do that, we're going to mention some assumptions that we need to have before we start trying to figure out whether we can estimate performance. Because if these assumptions are broken, then performance estimation becomes even harder, if not actually impossible. So our first assumption is that there is no concept drift. Concept drift simply means that the concept that our machine learning model has learned during training and development has not changed. So our conditional probability of the target given the feature vector is still the same as it was when we trained our model. This is an important assumption, but unfortunately, even if it's broken, we cannot do anything about it, since concept drift is something we can only measure when we have access to ground truth. And we actually do measure that with NanoML in NanoML Cloud. The second thing is we need to ensure that even if there is some covariate shift, and the covariate shift is one of the main reasons why our models fail, is that there's no strong covariate shift to unseen regions, the regions in your feature space that were not covered in any way during training. And just to define covariate shift here, covariate shift is just change in your joint distribution of your model inputs of your features. So anytime your feature drifts in one way or the other, this is just called covariate shift. And then we need to also assume that there's enough data to accurately model the concept, but this is kind of a given, since to deploy the model, we need to assume that we were able to accurately model that concept in the first place, so we can actually predict something. So these are the assumptions, and now let's go to the second part, which is how we can actually do it. Let's start with the intuition. So imagine that we have a very simple regression model that takes one feature, feature X, and then tries to predict value Y. And we see how the data is distributed here. And we see that there's a very strong linear relationship between X and Y. We're going to fit our machine learning model. Let's say linear regression here, because we don't need to use anything that's more advanced. And we have our model. This is the best possible model. It uses all information in the data that's relevant for best point prediction. But we see that there's also another thing going on here, which is the data dispersion, or the variance of the data, is also dependent on the value X. And if you look at the values close to 0, you see that dispersion here is higher, and it will also linearly actually decrease as value X increases. So intuitively, what we expect is that if we make a prediction here, we expect it to be very close to the actual value because the dispersion of the data is low. Whereas if we make a prediction here, we would expect it to have quite significant error actually. And if we do that, if we compute the mean error, mean absolute error actually, I should have renamed the plot here. If we calculate the rolling mean error when we order our data on the x-axis, and then we just compute rolling mean with window size 100, we actually see that this rolling mean error is going to drop as our feature X increases. So there's additional piece of information about this error that is available in our feature space that we cannot meaningfully use to predict the target in any way. And this is exactly the information we're using to build performance estimation algorithms. So we're trying to quantify this expected error, this uncertainty in some way, and then we'll leverage that to find some performance metric of interest. And to follow up on a slightly more relevant or maybe realistic intuition, imagine that we have two features this time, and we train a classification model, and then we're going to plot how it looks like. We're plotting here a nonlinear SVM. I think it's an RBF kernel. And you can basically apply the same reasoning. If we look at the places where the model is quite confident, it says that the class is most likely to be either class 0 or class 1. Then we expect that these places, the model is going to be very confident and also very performant, that the expected error is lower. So if you look at this area here, you can see that this is a high confidence area. The model is very confident there. And we can use that confidence as a proxy for uncertainty, which we can then transform in a quite smart way actually into the actual performance. Whereas here, if we're getting very close to class balance and there is negative and positive examples mixing together, this is low confidence area. This is where the model is very not confident about the actual predictions. So here, what we see is basically positive and negative class predictions, but instead of looking at it, what we are actually interested in is the actual confidence of the model. And the confidence of the model is basically just how close the prediction is to either 0 or to 1. So if the prediction is very close to 0 to 1, we're going to say that the model is very confident. If the prediction is very close to 0.5 for binary classification, then we say that the model is not confident. And it works exactly in the same way for multi-class or multi-label prediction. I'm going to be focusing on binary classification here, just because it's simpler to explain. But of course, we also focus multi-class. We also fully support multi-class prediction models. Okay, and here we see the exact same thing. You have this beautiful dragon fruit here, and we see that the red areas is where the model is basically expects to make more mistakes, whereas the green areas is where the model expects to basically have perfect predictions. And this is another way just to visualize the intuition I was talking before with the one-dimensional slides. Okay, so now what? We have this confidence. Then we need to talk about the covariate shift. So change in our feature distribution. And this is something that might actually happen, is basically guaranteed to happen if you have real life data that operates in the real world and has enough dimensions, that you will see that the distribution of your data shifts over time. And imagine that it just happens to shift to a region which is closer to the center here. So this our wonderful X or dragon fruit has more data points in the middle. And that means that we will see less points in the high confidence area when there's on average lower error, and we'll see more data points in the areas when there's higher error. So on average, our performance will drop. And this is again what we're going to leverage. And now let's talk about how we can actually figure out how to translate this expected error to the actual metric for classification models. So let's start just the definition of what is a confusion matrix, because this is what we base basically all our metrics on. So what we're going to try to do is we're going to try to estimate the confusion matrix for a given batch of data, maybe your last day of data, maybe last 10,000 points. We need to estimate it for enough data sample that's big enough so the performance is actually reasonably stable and representative of real performance, and that the noise doesn't dominate. And we actually get some kind of signal about the current performance of the model. So I'm going to try to do it for, let's say, last 10,000 data points or last 1,000 data points. And we're going to do it one by one by taking each prediction separately and doing some kind of magic with it. So ideally, what we'd like to do is we'd like to just fill in this confusion matrix with either zeros or ones. Unfortunately, this is not possible. Why is that? Because we don't have the labels. So we don't know whether this actual prediction turns out to be positive or negative. But what we can do is we can start with the fact that we take a single data point. This data point is a positive prediction, let's assume. So then we know that this positive prediction needs to be allocated somewhere here, either as a true positive or a false positive. We already know for a fact that we can allocate zeros to negative prediction because we know that the algorithm made a positive prediction. So we're halfway there, it's something. But now we also have additional piece of information. Most classification models, not all, but I think only most, return also something that's called predict probability, or some kind of value that normally is between 0 and 1, even though technically doesn't need to be. But let's assume for the time being that this value between 0 and 1, that's normally called predicted probability, is between 0 and 1. So one way of thinking about it is we could just put then, assume that this is a true probability, that it follows the definition of probability, which is over a long period of time, the predicted probability is 0.7 and we get 20 million points that say 0.7, we would expect 70% of those points to actually turn out to be positive. So then here, instead of taking the actual value, we can take the expectation over that, assuming that this is a real probability. And of course, it's not, I'll come to that later, but bear with me, assume for the time being that it actually is a real probability. In that case, we can actually allocate 0.7 of this one that we got, of this one prediction, to positive value, and 0.3, just the remainder, to false positive. And we're going to do that for our first prediction. Then for the second prediction, we're going to do exactly the same thing. Let's say that our predicted probability is 0.4. Let's say again that the model actually predicts negative for that case. And then I'm just going to allocate 0.4 here and 0.6 here. So we know it's a negative prediction, and this is the probability that it's actually positive. So we're going to have a false negative here and a true negative here. And we'll keep on doing that. For the third prediction, let's say we get 0.8. We just added to the first cell. We know it's a positive prediction. We have 80% chance that it's positive. So we add it here. The remainder goes here. And we keep on doing that. Let's say that for the time being, instead of going last 10,000 points, just for the purposes here, we want to estimate our performance for these 3 points. So what we're going to do is we're going to take this confusion matrix, this expected confusion matrix or estimated confusion matrix, and we're going to use it as if it was real. And we're just going to apply whatever metric we want. So if we do accuracy, accuracy is defined just as true positive plus true negatives divided by all negatives. All data points, which just gives us the accuracy of 0.7. And this is how we estimate performance with CBPE. This is the magic mechanism that allows us to take some confidence measure or uncertainty measure, like predicted probability, and then convert it into an expected metric. But as I mentioned, unfortunately, these numbers here are not actual probabilities. So we'll need to turn them some way in probabilities. Unfortunately, there is a method or a group of algorithms just for that. This is called calibration. So what calibration does is it takes the predicted probability, which is just an arbitrary number between 0 and 1, and turns it into an actual expected probability for a given data set and given data distribution. How does it work? So first, we're going to start with seeing whether these probabilities are actually probabilities. How do we measure them? So what we're going to do is we're going to take our, let's say, test set, some kind of data that the algorithm has not seen before, maybe first month of production. And then we're going to order all the predictions by the predicted probability. We're then going to bucket these predictions in, let's say, 20 equally sized buckets. The buckets don't need to be equally sized, but they might be. And then for each of these buckets, we're going to just measure the realized fraction of positives for the test set. So what you see here is so-called calibration curve. And what we get is, for example, for mean predicted probability of 0.3 bucket. So for this bucket, the average mean predicted probability is 0.3. We trained a support vector classifier here. And we see that the realized fraction of positive, if that was a real probability, should actually be 0.3, but it's not. Instead, it's something, I think, below 0.1. So we see that this number does not actually correspond to real probability. And what we're going to do is we're going to train a simple regression model. It will basically just straighten this line. It will fit it into a perfectly calibrated line, which is a line where y equals x. And there are some models, such as logistic regression, where you basically get this behavior out of the box because of how the machine learning model is specified. But unfortunately, for all the strongly expressive models that are used nowadays in machine learning, starting from any kind of deep learning to any kind of gradient boosting, whether it's XGBoost, LGBM, or whatever you're using, to any kind of ensemble models, you are very likely to get strongly uncalibrated predictions, which means you cannot treat these numbers that you get between 0 and 1 as actual probabilities. So how do we actually do it? How do we turn these predict probas into actual probabilities? We're going to fit the regression models, and this regression model is going to be very, very simple. And we can use any regression model we want. It can be an LGBM, it can be isotonic regression. So two typically used, just LGBM just because it's generally powerful, isotonic regression just because it has very nice properties that actually make sense here. One of those is that we assume that this function needs to be monotonic, and this function indeed does need to be monotonic. So we're going to take predict probas as features, so we have just one vector of features, just one dimension, and we're going to calculate what is the probability as a target that the target is actually one given our predict probability. So this is our target, and we just fit a regression line to it. We calibrated our probabilities. So now we can treat those numbers as actual probabilities. Of course, it's a regression model, so it's going to have some error estimated with it. So there's going to be some kind of miscalibration, but on average, we hope that it's going to basically cancel out. And there's, of course, some caveats. And there's two important caveats is that then if we do that kind of procedure, if we calibrate our model like that, we know that this model is calibrated if we look at the entire set at once. So in the aggregate, we know that the model is calibrated. But if we take it by any segment, if we only look at one class or one value of one of the categorical features we have, we don't necessarily get calibration. Whether that's important or not, we'll figure out later. Another thing is that we only get this calibration for the current covariate distribution. And this probably already gives you a small red light there because we just assumed that, or we allowed for covariate shift. So we allowed for change in this covariate distribution. And now we're saying that this calibration only holds for the current covariate distribution. So on like kind of a second level, we're actually imposing another assumption that we know is going to be violated. So let's see how it works, whether this assumption actually matters. So what I have here is just screenshots from our Animal Cloud. This algorithm is also available in the open source, by the way. And we have a way to measure a covariate shift that just takes into account the entire model input data structure. So we just measure how strong the data structure changes. We also have it described in details. It's called PCA reconstruction error. I won't be going into detail here. Suffice to say that it's a way to measure the strength, the magnitude of covariate shift in one number. And we see here that we don't really have a strong covariate shift because it doesn't change from the test set. And the test set is kind of our reference set for which we always assume that everything is fine. So if this value is fine for the test set, then we also, once we put it in production, this part is the production value, the value that we haven't seen, then the predictions that we did not train on, did not test on, these are actual numbers that we use to make predictions in reality. We see that this PCA reconstruction error, so the measure of covariate shift, is not really changing. And if that's the case, so we don't have very strong covariate shift, but we have some kind of covariate shift, we do see that CBPE is great at estimating accuracy. And you see that it basically the line of estimated and realized accuracy follows perfectly. And there's also one very interesting thing to see that even if we don't have covariate shift, we can still see a significant drop in performance. And the drop in performance is really significant here. It drops by almost 10 percentage point. 10 percentage point change in accuracy is definitely something that the business should know about. So we see this drop in accuracy here, which is also another reason why you always need to estimate performance and not just rely on data drift signals, because your data drift signals can be quiet and there's still significant issues. And of course, vice versa, there might be potential issues with covariate shift. There is some kind of covariate shift, but it actually doesn't impact performance that much. But we see that for small covariate shift, CBP works reasonably well. Now, let's take a data set. These are all real life data sets. And we see that there is some kind of strong covariate shift around beginning of July, let's say. And here, CBP is able to detect that there is indeed a change, but it underestimates that change quite significantly. So it only detects one batch of data where the change was actually significant enough to trigger an alert. whereas the problems actually already started a few batches ago, and they are stronger than expected. So it is directionally correct. It tells us something. It is still useful, but it doesn't tell us the full story, and it might not be enough if our use case is very important. We also see the confidence bounds would tell us possible range of performance. This is something I won't be covering here, but we also have an algorithm that estimates this this confidence bounds. And we see for 2 points, it actually goes out of the confidence bound. So we see that for strong covariate shift, also these confidence bounds cannot be fully trusted. So we see that there is an issue with strong covariate shift. Now, we already talked about that we have potential assumption that we're violating about calibrating the model, and the model is only calibrated and can be only used to do this magic trick when we take the predicted probability and transform it into performance if there is no strong covariate shift. So let's measure how it actually impacts calibration. So what you see here is the same calibration curve that I showed a few slides ago, but just for this model that we trained that you just saw above, on the first data set on the analysis data, so we're only showing it how it actually behaves after the model has been deployed. And the calibration here is basically perfect. It's still like slightly S-shaped, but nothing to worry about. This is good enough. Whereas if we look at the second data set when we experience very strong covariate shift, and I was actually surprised, like properly surprised to see how bad it gets. I was expecting that it's going to be like more S-shaped than this one, and it gets miscalibrated a bit, but we see that calibration here is absolutely terrible, even though we did calibrate that model on our test data. But once it's been deployed, we've seen that the calibration is completely ruined, and we should not be using that to estimate performance. We did, and we still got some kind of information, so we see that CBP is in some ways a bit robust to covariate shift, but once covariate shift gets strong enough, it starts to be very inaccurate. And one note here is that the effect of this miscalibration performance is complex, it's strongly nonlinear. You cannot really just draw any kind of simple way that you measure some kind of calibration error here and then you try to push it to performance error. There's few more things there. It's also a very nonlinear effect. So let's kind of finish looking at CBP by looking at the last thing, which is how well does it handle small data? Sometimes we won't have the luxury to actually have access to a few thousand data points per every chunk. Maybe we get only a few hundred data points every week, and we really need to know the performance of our models every week. How does CBP deal with that? Here, there's good news. We actually see that CBP, if we take a data set and we chunk it, or so we use batches of 250 data points, the data set is actually, the CBP is actually very good at estimating those. If we use bigger chunk size, then the data set, the CBP is still equally good at estimating those changes. So if we want to work with small data, we can use CBP. And these screenshots are, by the way, I think from our open source, so it looks slightly different just for a bit of variety added. So now let's talk about how can we potentially solve the problems with not having good calibration. And the way to do it is try to calibrate potentially with respect to many things at once. But before we go there, let's try to kind of understand how is it even possible that we calibrate our model, then we see no concept drift, so the actual pattern between the model inputs and the targets does not change, but we still lose calibration. And I'm going to give you a simple explanation here. So imagine we have a feature in our data set, which is a binary feature, and it can have value either blue or red. And it just so happens that 90% of the data points in our data set are blue, and the remaining 4 are red. Then we're going to calibrate our model, and because I mentioned that the calibration only gives us guarantees on the average, we know that for the average calibration, let's say we get like actual perfect calibration, but it might happen that the blue, if we take just the blue segment of the data, which is 90% of our data, it's going to be slightly miscalibrated. It's going to have a shape like that. And for the red part of the data set, it's going to be terribly miscalibrated. It's going to be like the predicted probabilities won't really mean anything. And the good news is that on average, when we construct our partial confusion matrix or instance level confusion matrix and we start adding things, these errors will even out. And as long as we get calibration that's good on average, we're also going to get estimation that's good on average. However, imagine now that we undergo covariance shift, or the data set undergoes covariance shift. And what we see is that now we have 90% of red values, but only 10% of blue values. Right now, the miscalibration of blue segment and the red segment does not cancel each other out anymore. And together, on the average, we actually see that the data set has become very strongly miscalibrated. And this is kind of the intuition of why just pure covariance shift can actually influence calibration, and why that might mean that CBPE will stop working as well as it used to. So how can we solve it? The simplest way to do it is we can look at all our segments in the data, all categorical features, and we can potentially, if our data is big enough, try to calibrate each of those segments separately. Then, even if the composition of those segments shifts as we deploy our model to production, we have nothing to worry about because they are all separately calibrated. Unfortunately, this is literally impossible in practice. And there are multiple reasons. First of all, how do we use continuous features? The data can also shift along the continuous features. Maybe first we were dealing with a population that was mostly in the 20s. Now our customer base is mostly in their 40s. What do we do with that? How do we segment that? How we try to calibrate with respect to different segments at the same time? We need to impose arbitrary lines. And if the range of this continuous feature is big enough, we might not be able to have enough data to actually do proper calibration, because remember, it's still a regression model. We still need to have enough data, generally speaking, at least 1,000 points to fit it well. What about imbalanced features? If we have a categorical feature and one of the categories only happens in 0.001% of the cases, we're almost guaranteed to not have enough data for that specific segment to calibrate it separately. And last thing is that the covariance shift might happen not along an axis of one specific feature, but it might happen along the combination of features. So the only thing that drifts is, for example, that we have more people who are at the same time old, rich, and green, for example. Then again, if we look at this subset small enough, we will never have enough data to actually calibrate it. And there is a solution, but before I go into the solution, let's try to figure out a different approach that will actually give us the tool to solve this problem. And this different approach is importance weighting. So importance weighting is a surprisingly simple algorithm that's surprisingly hard to explain for me. And it only takes 2 steps. So before I go over the steps, let's first talk about what we intend to do. So what we intend to do is we're going to take our test data set, and then we're going to try to reweigh the performance on that set so that it somehow resembles our current batch. So we're going to weigh higher the data points in our test set that look like the data points in our current batch, and we're going to assign a lower weight to data points that look different in our current test set than our current batch. So we're going to basically assign some kind of importance, the weight, to every data point, and then we're going to use our labeled test set to just compute performance. And of course, the big part here is, how do we assign these weights? How do we even try to quantify this change in distribution in a way that we can come up with those weights? And these are the exactly 2 points. We're going to try to quantify that change in distribution. And again, here you see just 1D example, but we might be dealing with thousands of dimensions, so it's not going to be that trivial. And then another thing we're going to do is we're going to reweigh every point in the test set by how important it is. I know it's vague, for the current batch, and then we're going to just calculate the performance kind of as if the test set looked like the batch. So let's get started with the first part. And the way we're going to do it is so-called density ratio estimation. So the kind of explanation is in the name. What we're trying to do is we're going to try to estimate the density ratio, the ratio of densities of the test set and the batch data for every data point in our feature space. And it's important to notice that we cannot just assume that the data points will occupy the exact same spots. So we need to have some kind of function that will be able to tell us this density ratio for any point in our model input space. So we will need to train some kind of model that will approximate this ratio, because we won't have data in exactly every point in our data, in our model input space. So how do we do it? Just a small tangent before, we could alternatively just try to estimate the densities for each of the data sets. So the test set and our current batch, and then we could divide one by the other. But that is a bit more unstable, because if we have very little density from one of the data sets and we divide by it, then we're going to multiply the errors and we're going to get very unstable predictions that don't really work well in practice. So instead, we're going to try to directly estimate this ratio. How do we do it? We start with a binary classification problem. We're going to discard all the all the labels, because remember, for our current batch, we don't have access to the labels. We're going to try to estimate the performance without having access to the labels. This is always an issue. So we discard all the labels. Then we're going to say that if a data point comes from the test set, this is a negative class. If it comes from the current batch, it's a positive class. And then we're going to use all the model inputs as features. And then we just train the model. So we get the probability that a given data point belongs to either the test set or the batch set, given all our model inputs. And then we're going to compute the function from that prediction that will actually give us these density ratios. And we're going to do it step by step here. This is the part that's slightly complex, so bear with me. What we need to do to compute this weight is two elements. The first element, which is kind of easy to understand, is that what we need is we're going to basically take the probability that a given class belongs to the batch at any given point, and we're going to divide it by the probability that this specific point, given x, belongs to the tests. So we basically just divide this value by this value, which is what you see here in the visual explanation. And another thing that we need to do is we need to normalize by the number of data points in the test set and the batch set, because if we don't do it, the model is very likely to say that everything belongs to the test set, or it's more likely to belong to the test set. So this can be formally derived using Bayes' theorem. It's not that hard, but here I just want to give you an intuition. So we're going to also divide it by the number of data points in the test set by the number of data points in the batch. And this is the weight we get. And then we're going to use that weight when we just calculate performance. Let's say we calculate accuracy. So every data point, we're going to do it on the test set. And every data point in the test set, for every data point, we're going to calculate this weight. And then we're just going to apply it as the importance of this data point. And we get our metric. So we don't have to talk about probability here. We don't have to talk about calibration. It's a completely different approach. Let's see how it works. So again, I use the same data sets here for small covariate shift. We see that the model performs very well, and sometimes you get like a bullseye, basically. This is a perfect prediction. For very small changes, we get slightly higher error than CBPE, but generally it's comparable. Slightly better here, slightly worse here. It's fine. And good news is that even under strong covariate shift, because we don't have this additional hidden assumption, the model is quite good at predicting what's going on, and it can actually estimate even big changes in performance that happen due to big covariate shift. But there's an issue, and the issue is small data and small chunk sizes. And this is something that unfortunately happens quite often with models in production, that you don't make that many predictions every week or every day. And here, if you see the big chunk size, everything's fine. If you look at the small chunk size, it's potentially not that obvious to see, but you see that the dark blue line, which is the realized performance, and the light blue line, or teal, I think it's called, which is the estimated accuracy, they don't actually follow each other very well, and the model is kind of doing random things. It still follows reasonably well the actual trajectory, but it's nowhere near as good as CBPE, which was basically perfect here. So we solved one problem, but we introduced another. And now, as we slowly get to the end of the workshop, let's try to combine these two ideas. And the way we combine it is the M-CBPE algorithm. Before I go there, I just want to make sure that everyone was able to follow. So if you have any quick questions here, go ahead, because this part is we will really be putting everything together. So I want to make sure that you are able to follow. No big questions, I'm assuming, Mafalda, just to double check.
Yes, perfect explanation, apparently, Wojtek.
Or
No,
everyone is so lost they don't even know what to ask about. It's another option. Okay, so let's continue then. So we have M-CBPE. And what we're going to do here is we're going to take our CBPE, and instead of trying to figure out a magic well to calibrate it with respect to everything at once, we're going to forget about it, and we're going to just calibrate it with respect to current batch. But we don't have labels for the current batch, and to do calibration, we're going to need those labels. So what we're going to do is we're going to apply importance weighting, not to calculate performance, but to calibrate the model. So we're going to apply these weights that we just calculated. We calculated in the exact same way, and then we apply to our regression model to the importance for every point as we train our regression model to actually calibrate the original model. So we're going to do this calibration on the test set, but we're going to kind of make it look by applying these weights as if it is the current batch. And what does it mean is that no matter how the current batch works and how it looks like, we don't need to calibrate it to a million different ways. We just calibrate it to the current batch using importance weighting. And then for the current batch, we have guaranteed that no matter how it looks, it's gonna be approximately calibrated. So without calibration on the current batch, if we just calibrate it without these weights, it will look like this. But now we see that there is more blue data points. So we're gonna weigh them more, and we're gonna then get still good calibration. So that is really how we put it together, kind of a simple thing, but we need to put it in the second part of the algorithm, just only applied to the calibration. So we get rid of this violated assumption, because the calibration is done as if there was no covariate shift, because what calibration sees is the actual current batch and not the test set. And of course, we still need the assumption that there is no concept drift, because we're going to be using the targets from the test set. So the pattern, the concept between the model inputs and the target still needs to hold, even if the model inputs are distributed differently. So we got rid of the caveats. That is we calibrated with respect to something else, so the caveats are actually not problematic, because now the probability distribution is calibrated for the current batch and also for the current covariate distribution, which is exactly what we're interested in. And we're going to do this calibration again for every batch. So it is slightly more computationally expensive, roughly the same as importance weighting, because for importance weighting, we also had to do it for we had to compute these weights for every batch. A CBPE is much cheaper because we need to do one big thing only once, which is the calibration. Here we need to compute the weights, which is quite expensive, and do the calibration, which is reasonably cheap for every batch. But let's see if it's worth the additional computational effort or computational cost. We see for small covariate shift, it's basically exact same carbon copy as here. It's like a small difference, but exactly the same performance. However, for big changes in performance, if you compare it to CBPE, we've seen that the performance is actually much closer to the realized performance, and the algorithm is able to capture that, and it gives us the alerts every time that there was an actual issue. It's slightly underestimated, but we see that every single data point in our data set is actually well within the confidence bound, and we can actually say that this is a really good way to estimate performance. Let's see if we managed to solve our second problem, which is small data, which was a big problem for importance weighting. And again, we did. We see that basically you have perfect fit between the estimated and realized data. If you compare it with this here, you can see that basically there's no overlap between the teal and dark blue lines, whereas here the overlap is basically perfect. And that is really it. So